Now it's a pleasure to introduce one of our own, Associate Professor of Earth Sciences, Lesley Sonder, to introduce our distinguished speaker. And I really want to thank the Earth Sciences Department to supporting our Wetterhahn Symposium this year. And a little bit about Professor Sonder, as she is in her 25th year of teaching here at Dartmouth, got her undergraduate degree in Earth and Planetary Sciences at Washington University, got her PhD at Harvard in geophysics. She grew up in Oak Ridge, Tennessee, in a scientific family. Both parents worked at Oak Ridge, her entire family of scientists. And outside of the classroom, she loves her viola and she loves to row. And Lesley, it's your opportunity. Here.
So let me start by saying that geologists always say that the present is the key to the past. What we see today informs how we interpret the past. So I'm going to start in the present now to introduce Terry and work my way back in her life. Terry is currently professor at Columbia, really at Lamont Doherty Earth Observatory. She's been there since 2008. And before that, she was professor at BU and at Kansas. And her work has taken her all over the world. Here she is, if you can see it once we get there, about to take off for fieldwork in the Aleutians. She has worked everywhere from Central America to the Aleutians. And basically her work involves magmas and volcanism. Basically she's trying to understand how magmas form, how their formation and their character influence eruptions and the character of eruptions, the explosivity and so on, and how, what are the sort of the interactions between the Earth's interior chemically and the surface of the Earth chemically and how they feed back for each other. And she'll be talking more about that later. But she's, in this career, she's the winner of many, many awards for her work. Just most notably and most recently, she's a member of the National Academy of Sciences, and she was recently named a MacArthur Fellow, the so-called Genius Awards. Going farther backward than from there, Terry, many of you don't know, well, let me work backwards. She did her PhD also at Lamont at Columbia. And before that, many of you don't know that she is somebody who has granite in her muscles and her brain. Terry is a Dartmouth alum. She was class of '85. Here she is on the Earth Sciences Foreign Study Program, the Stretch. That's her in the front row in 1983. And she, like many of you all, she was involved in research as an undergrad, and she did a senior thesis. And I managed to find a copy of her senior thesis, if this, oh, there we go.
I published it.
There she go. Well, I went back to Kresge and looked at your that's her title page in the pre-Microsoft Word days. She probably typed the whole thesis. And when I was leafing through it, I was struck by a couple of quotes in there, which you can read in there. And I think there's a lesson for all of us in this, and especially for those of you who are just setting out in your first research. It's essentially one of making scientific lemonade from scientific lemons, so to speak. If your results are confusing, if the simple or the straightforward explanation doesn't work, maybe there's something that's really to be learned and really to be gained from teasing out the complexities of the data. And Terry says that several times in her thesis. But this ability to tease out the interesting from the complex, to tease out greater insight rather than lesser insight. Perhaps that's why Terry has been so successful in her career. And with that, I think I will leave Terry to tell us about her career. So thank you.
Glitching, though, I think.
Let's see if I can help. It's over here. They may have just done this. Yeah, I think they just. There we go. No, it's that one. Sorry. That should.
Oh, no. There it goes.
Yeah, there it goes.
All right.
I don't know what's happening with that.
The room will self-destruct in 5 minutes.
Anyway, you have your.
That's fine. Am I on sound? Yes, okay, you can all hear me. It's a total pleasure to be here. Lesley just killed my joke. I was going to talk about granite in my muscles and my brains, which, that's okay. It's just much more literally close to me because I really did work on the granites of New Hampshire and even write a paper on it. I also had the pleasure of taking freshman chemistry honors section with Karen Wetterhahn, so this also means a lot to me. And it's so great to be here. I'm also going to show this amazing stretch picture. Oh, wow, now we're in we were in stereo here. We look like a bunch of derelicts here on the shores of Lake Powell, but I want to assure you that several people have gone on to have careers in earth science from this group. I know 4 still who are in the field. Guy back here is Johan Ekstrom, who's teaching in a college in Maine and lives in an island in Maine. And Jennifer Reynolds, who's back here, is an associate director for undersea research, a part of NOAA at University of Alaska. And I'm standing here, and then I'm standing next to the great in stature Jake Lowenstern, who turns out to be the volcanologist in charge of Yellowstone Volcano Observatory. He's probably the most important person here, who's going to save us from demise of the human race. Anyway, the Dartmouth Stretch, as many of you may know, moves students for a whole semester through a bunch of different geological terrains. And it originated really as a volcano program, from what I understand. Professor Richard Stoiber, Dick Stoiber, took the men of Dartmouth, as it was back then in the late 60s and early 70s, to Guatemala, really, to map volcanoes. And that was the whole stretch. It was pretty basic, I think. And since then, it's grown to include lots of different places and geological settings. When I went, we went out to Wyoming, and we were on those houseboats in Lake Powell. Oh, I forgot to point out, yeah, this real derelict was Edward Abbey, who was the environmentalist activist who went out with us, the guy who wrote the Monkey Wrench Gang and Desert Solitude. He was a total grumpy guy. But it was still pretty cool to have him out there. He thought the Grand Canyon was already ruined, so he just wanted to go out there and see how terrible it was that Lake Powell had flooded his beautiful Grand Canyon. But it was interesting to be out there with him. So we also got down to volcanoes after seeing mines in Mexico. Being in the 1980s, most of Central America, which is where Dick Stoiber had taken people, was in conflict. We couldn't even fly over Nicaragua airspace, so the only place we could go was Costa Rica, which at that time, as it is now, is a peaceful and well-organized place. And we got to visit 3 active volcanoes, which were all in national parks, so they're accessible and well-preserved. One of them was Arenal Volcano. Who's been to Arenal? Yeah, a couple people. It's a beautiful tourist destination. These days, you can sit in a hot tub and watch it erupt. But when I was there was the bar. That was it. There was the bar in Fortuna. We went, we ate at the bar, we drank at the bar, and we slept over the bar. And it was really, really pretty low. I got attacked by mosquitoes that night, and I brought back to Dartmouth a human botfly larva, which was only discovered after every single doctor at the Dartmouth Medical Center came to gape at my tropical parasite. They were so excited in the dead of January to have something really cool to look at. It was harmless, but it was my souvenir back from Arenal. We also got to hike up, though, and see an active lava flow, which is cool. It wasn't as cool as Poas Volcano, where we got to hike down in the crater. And it didn't look like this. This is actually a recent picture. Poas has erupted 11 times since we were there, so the crater's been remade several times. But we got to hike down into the crater, which not everybody gets to do, and hike up on this steam bank, this fumarole bank, and wear protective breathing apparatus and sample the hot gases. That was really exciting. And then we also got to Irazu Volcano, which wasn't erupting as spectacularly as the other 2, but it's at 12,000 feet, and you can see the Atlantic and the Pacific from the top of it, and it's just a gorgeous place. And what was most memorable about Irazu to me, however, was a lecture that happened at the foot of Irazu the day before. This was an assistant professor, Barbara Barrero. She was not here that long. She was giving a lecture outside with a paper and easel, an alfresco lecture, talking about the volcanoes of Central America. and pointing out that we were really on top of a subduction zone, and nothing brings that home like sitting on a volcano and being able to look out into the ocean. So here's Costa Rica, here's a whole line of volcanoes, and these are produced by subduction of the Cocos Plate, which is the Pacific Ocean seafloor, the Cocos Plate converging against the Caribbean Sea Plate, and the Cocos Plate gives way and sinks underneath, and produces this trench, the Middle America Trench, earthquakes, and the line of volcanoes. Irazu is the last one, so it's kind of special. It's the last volcano in Costa Rica before there's a couple in Panama. And Barbara said at the time, we don't really know why subduction generates volcanism, and I just thought that was so cool. And she had come back from being a postdoc at the prestigious Carnegie Institution of Washington, where scientists had done this very interesting experiment to try to connect volcanoes to the subduction zone by tracing material through the process. And they used an isotope, beryllium-10, which is like carbon-14. It's cosmogenic and generated in the atmosphere. It rains down onto the surface of the Earth. Unlike carbon-14, which gets taken up in plants, beryllium-10 gets absorbed into sediments, including sediments on the seafloor. And the seafloor, as I said, is subducting and taking those sediments into the Earth. And if material is returned in volcanism, then we might see beryllium-10 in the volcanoes. The key is that beryllium-10 is also radioactive with a fairly short half-life of about 1.5 million years. And so it doesn't accumulate in anything. It's only in the uppermost sediments on the seafloor. It doesn't exist in the Earth's mantle. It's only a tracer of surface material. And to be able to see it take the round trip and come back out the volcanoes is remarkable. These scientists looked at volcanoes at other places. They only found beryllium-10 coming out subduction zone volcanoes. And for many of us, this became the smoking gun evidence that volcanism is indeed connected to the material being subducted beneath it. And it really set the course for my career, this lecture. I remember this really vividly in the jungles of Costa Rica, Barbara Brower and beryllium-10. And so I've really spent most of my career chasing all of this around a subduction zone. For about 20 years, I've studied both the inputs, that is the sediments and the ocean crust that are actually sinking into the Earth. I've been out on 2 drilling cruises to drill the material in the incoming plate. I've drilled the oldest crust in the oceans outboard of the Marianas Trench. Just to see what's going down the tubes. And then I've worked with experimentalists in the laboratory to then inflict upon that stuff the high pressures and temperatures that they experience as they are taken into the subduction zone, and how they transform, how the minerals transform and are carried into the deeper Earth, and how they generate fluids, which may be the transport agent to return to the surface and drive volcanism. And then I've spent a lot of time studying the volcanoes. I've just counted this up. I think I've published on 40 different volcanoes. And I've been really using them as probes of what's happening underneath, what's driving the melting process, and again, what the connection is with the subduction zone. That's actually what characterizes and probably what people know me for. I'm not going to talk about that today. I'm going to talk about something else that has to do with the gases that come out the volcano. So that's kind of what I've been doing for the last 10 years. What causes the melting and what drives the circulation is actually water. It's water from seawater ultimately tied in minerals in the downgoing plate that get subducted, drive melting, come out, and then fuel the eruption. I got to thinking that water is really everything, and I shouldn't be wasting my time measuring anything else except water. And I'll talk a little bit about that today, and actually more about that tomorrow in the Earth Science Seminar. And then what I've really been working on the last year or so that I'm going to talk about is the eruption. And maybe you think this is stupid that it's taken me so long to actually work on the thing that's important. But I was more interested in just how the Earth worked and using volcanoes as probes, and not, the eruption was kind of a nuisance. You don't want to go sample a volcano while it's erupting. It's dangerous. I go when it's after it's erupted, and then you can pick up all the rocks in safety. So that's what I've been doing. But I came to understand from teaching enough about eruptions and then connecting it to the water work that we're doing that we have something to contribute to that. And that's what I want to talk about today, the work that we're doing to really understand what drives explosive eruptions. This is a photograph of the eruption of Mount Redoubt in Alaska in 1989. And it's famous because it's one of the first times an airplane unwittingly flew into a volcanic ash cloud. It was December, it was dark, so the pilot couldn't see anything. It's December in Alaska. She knew that there was a volcano erupting near Anchorage. She thought she had given it a 150-mile berth, which was enough. but evidently it wasn't. And what I have here is the really loud. It's hard to hear, so I actually have the transcript. So she's flying in and noticing that there is something. I love how she's just descending. So you could hear her voice go up and up and up as that happened. And I could have you sit for 4 minutes here because that's how long it took for the plane to go in free fall until the engines regained. People were weightless in the cabin, and they were smelling sulfur, and they were throwing up and panicking. You could imagine how everyone felt with this airplane where all the engines had flamed out. But the pilots kept trying to restart the engines, and they actually did. Really, though, within only a few thousand feet of the local elevation, because there are mountains all around Anchorage. They were flying into Anchorage. But the plane did ultimately land safely. It wasn't easy because all the front windows had been sandblasted by the ash, and so she had to fly by looking out the side window, and she couldn't reach the controls from the side window, so had to look and communicate to land the plane. It wasn't easy, but they landed safely. The airplane, of course, sustained $80 million of damages, which is something to think about when monitoring volcanoes in Alaska costs about $1 million and is being cut right now. So this was a wake-up call. Readout stands as kind of a symbol of this. And it started erupting again in 2009. And this is when I learned that being in New York means that you're automatically an expert on anything, and some news station's going to call you when anything happens. And so I got put on TV. I have worked on Alaska volcanoes.
And immediately lost power in all engines, fell almost 2 miles in altitude before the engines regained, and everyone landed safely eventually in Anchorage. But this was a big wake-up call to the aviation industry and monitoring of volcanoes in Alaska.
Well, that was like a stereo event too, except I have a lot more makeup on there. They sent a limo to my house and threw me on TV. I'm never going to do that again. It was terrifying. Who's ever flown to Asia? Yeah, okay. So if you fly anywhere to Asia from North America, the closest distance on a globe is actually a great circle that puts you right over Alaska. It's not over the Pacific like you'd think. There's 40 historically active volcanoes in Alaska. And so given the number of passengers and cargo, it's been a great development to set up monitoring, that is individual seismic stations on all the volcanoes of Alaska. And that process is still happening and also being cut to some degree as well. And this, of course, wasn't a wake-up call in just Alaska. We all know about the unpronounceable volcano in Iceland, too. Eyjafjallajökull. Okay, I'll try. So it erupted. It was a pretty small eruption, but the wind was blowing just the right way to, of course, shut down airspace in Europe for a week and estimated billions of dollars of loss to the economy, and not to mention lots of inconvenience to travelers. So we live on a planet with eruptions, and you might think living in New Hampshire, who cares? But volcanic eruptions like this can affect everybody. Oh, wait, I missed my movie. No, that's okay. So we might ask then, what else volcanoes do to us? And I figure you came to this lecture to some degree if you came at all to hear the talk. I'm talking about volcanoes. It's exciting, and maybe you're hoping I'm going to show pictures of devastation and destruction. So let's just actually talk about this. What are the 3 ways to die in a volcanic eruption besides being in an airplane? And you might think the lava is really bad, and it is. You know, in Hollywood, if somebody chucks you in a vat of lava, you'll definitely die. But usually nobody throws you into lava flows. It's 1,000 degrees. It would incinerate you. But do these guys look concerned? No. So most lava actually has the consistency of ketchup, and you can easily outwalk it. There's some extremely fluid lava that can inundate. It's inundated some towns in Africa, and certainly there's been a lot of damage in Hawaii. But most lava flows are not the danger, despite the excitement about them. You can walk away from those. No, the things that kill you are flows that travel much faster than you can run, that overtake you. They're pyroclastic flows, which will fry your lungs. Lahars, which are mud flows, which can bury you alive and sweep your town away. And a tsunami that will clearly drown you. Now, you know what tsunami are. I'm not going to talk about that. We've heard a lot and seen a lot about tsunami from earthquakes, but volcanic eruptions that happen on islands also generate tsunami, like Krakatoa did in the 1800s. I'll show you briefly, though, something about pyroclastic flows and lahars, because those are unique to volcanic eruptions. This is a pyroclastic flow.
200 miles an hour. The town's firefighters make a mad dash for safety, knowing that anyone caught in the cloud's killer path will not survive.
So it's,
no lives are lost during
well,
this frightening natural disaster.
some lives actually were lost in this natural disaster. This is a very hot cloud of gas and ash that's moving at tens of miles an hour and can overtake you, and it leads to immediate death if you're trapped in one of these. This is the eruption of Unzen in Japan, and 40 people did lose their lives in this eruption, including 2 famous volcanologists. Of course, the famous eruption that killed lots of people in pyroclastic flows was Mount Vesuvius in 79 AD. This is Pompeii and Herculaneum. Those are not statues. Those are the hollowed out forms of bodies that were preserved in the pyroclastic flow deposit itself and then filled in with plaster to show their positions at time of death. There's some debate as to whether you're incinerated by the pyroclastic flow, because it can be up to 700 Celsius, and that would kill you, or whether it's asphyxiation from breathing in the ash, which then mixes with the mucus and causes asphyxiation. Either way, it's a bad way to go. And you might think, who's stupid enough to live next to Mount Vesuvius after Pompeii? Well, of course, 3 million people live in Naples. There's Mount Vesuvius. Pompeii was on the other side. Naples is on this side, Napoli. And this is probably, for this reason, Vesuvius is considered the most dangerous volcano in the world. Not because it's the worst, but because there's so many people in harm's way. Lahars are hot mud flows. You are still sleeping. River of hot mud and rocks sweeps your house away. You can tell I had a liberal arts education. That's a haiku. Dartmouth. So this is what a lahar looks like. They can be hot. You don't need to hear the sound here. Yeah, it can be hot. It can be boiling mud, but that's actually not the issue. It can be completely cold, but it's so full of boulders and ash and sediment that it's basically a giant flood that comes racing down a volcano, especially a volcano that's had eruption under ice, or in the case of Mount Pinatubo, a typhoon hit the volcano after it erupted and launched lahars. They pretty much wipe out everything in the river valleys below volcanoes. 30,000 people died in one town in Colombia in the 1980s. And again, you might think, who's stupid enough to build a city near a volcano that has lahars? Is anyone from Seattle? Seriously, there's nobody from Seattle. All right, well, they're all staying there, I suppose. The Mount Rainier is actually a volcano, and when it erupts, and it has in the past 100 years, it will launch lahars.
Is there one impending volcanic eruption that we should be worried about that we may not be thinking as much about as we should?
Probably in the US, the most dangerous volcano is Mount Rainier outside Seattle. Mm-hmm. There's big parts of Seattle and Tacoma that are actually built on the deposits of previous eruptions. so that's always bad. There's tons of ice on top of Mount Rainier when it erupts, and it will launch large mud flows that potentially can wipe out large portions of Seattle and Tacoma.
But the time scale we're talking about here, though,
Oh,
we take some comfort there.
Well, it could wake up tomorrow. No, it's dormant to some degree, but it's had eruptions in the past few hundred years. It will erupt again.
Well, thanks for alarming all of our listeners.
Volcanoes certainly do wake, and we know they're unlike earthquakes, which are inherently unpredictable. Volcanoes erupt with lots of warning signs.
Yeah, okay, I'm never going to go on NPR again either. I talked about all sorts of important things that had to do with science, and that's the only thing that made the interview, was saying that Seattle was going to get wiped out. But it wasn't entirely wrong. This is the map I got from my friend at the USGS, Tom Sisson, where Jake Lowenstern works. He's down the hall. He's the volcanologist in charge of Rainier. And he's mapped all the mud flows. That's what these black regions are. And this kind of gray shading is where there's a high population density. And this is Tacoma, this is Seattle. So I-5, the airport, the port, totally wiped out, and not to mention a lot of communities. There's not really much we can do about this. This will happen unless we move the houses out of the way. So let's just hope this doesn't happen at nighttime. That's the worst disaster in the US. Okay, so we've seen a bunch of interesting and explosive eruptions and the phenomena that they launch. We know this also happens. This is Hawaii. And it's just a tourist destination. It turns out Hawaii used to erupt explosively 100 years ago. There's ash deposits all over the island, and it would shut down airspace in the Pacific if it did it again, Kilauea. So there's a volcano that actually has flip-flopped between effusive, peaceful eruptions and explosive ones. So you should be thinking right now, besides the death and destruction, why are some eruptions more explosive than others? Why is Mount St. Helens? The VEI scale is like the earthquake magnitude scale, so it's an order of magnitude scale. This is 4 orders of magnitude larger than a Hawaiian or Iceland type eruption. So why are some volcanoes more explosive than others? And the first reason for this is, this comes from physics, and the best way to demonstrate any kind of physical principle is with a kitchen example. So a seltzer bottle is a perfect volcanic eruption. Well, that was a VEI 1, I think. That wasn't a very big one. And so, what happens is the gas inside a seltzer bottle is CO2, okay? CO2, and when the cap is on, it's under pressure. So the solubility is higher under pressure, so the CO2 is dissolved. You take the cap off, you lower the solubility, and the CO2 comes out. And when it comes out violently and there's more gas than liquid, that's the definition of an eruption. The same thing happens in an eruption. There's more gas than liquid magma being thrown out, and that's what causes ash and plume clouds. So the seltzer bottle is a good analogy. It's our first way of thinking of volcanic eruptions, and it's been the way that we've been modeling how some might be more explosive than others. Maybe it has to do with the gas content. Now, in volcanoes, the gas is water, not CO2. It's water. And where does the water come from in volcanoes? Well, I already mentioned it. It comes from the ocean itself, not because volcanoes are on coastlines, but again, through plate tectonics. Volcanoes are on tectonic plates, and I showed you the subduction zone. We actually literally subduct seawater, which is trapped in minerals and sediments on the downgoing plate, taken into the earth, where these minerals break down at high pressures and temperatures, and dehydrate, release the water. Water lowers the melting point in the mantle and drives the magmatism, and then exsolves as bubbles, just like the seltzer bottle, to fuel the eruption. That's our physical model from the seltzer bottle, and then coupling that to plate tectonics, delivering the water. But nobody's actually ever tested that, because it's really hard to measure how much water erupts from a volcano, because it's gone. It's like the seltzer bottle. How much CO2 is in the seltzer bottle before you took the cap off? It's gone. The same thing in a volcano. All we are left with is rocks full of holes where the gas used to be. You could try to add up all the holes, but that's a really difficult calculation because it's a huge volume change to know how much used to be dissolved as liquid water. So what we've come to figure out, and really only in the past few years, is that we need a little messenger. We need something, like think of something going into the seltzer bottle to to protect some of the seltzer before you open the cap and keep it under pressure. Like a little, and what we use are little crystals. These are crystals of the mineral olivine, which crystallizes from the magma. And when it crystallizes, it accidentally encases some of the liquid. And if that happens under pressure, it's happened before we've opened the cap or before the magma's depressurized. And so it still has all the water dissolved in the magma. It erupts, and the magma quenches into a glass. So that's what you're looking at is a yellowish crystal with brown glass. That's some of the brown glass. That's brown glass. These are called melt inclusions. And they're quenched into glass, and then we can section them and analyze them to see how much water was in the magma under pressure before it did its exploding. And so that's what we've been working on. We have to go out and actually collect dedicated samples for this. Lava flows turn out to be bad because the water can diffuse out of those crystals in the time it takes for lavas to cool. So we've gone out to just look at various volcanoes. One is Seaguam in the Aleutians. We've studied about 7 or 8 volcanoes in the Aleutian Islands of Alaska. Lesley showed the helicopter picture, but here we had to go by boat. We got on a fish and wildlife vessel here and took several days to steam out. We really hitchhiked with a bunch of guys who were counting birds. And they took us out to Seaguam, which had this eruption in 1977. We sailed past one volcano and another every couple hours. It really makes you believe in plate tectonics that we produce a line of volcanoes. That's Seaguam today. All these black things are the 1977 deposits, so we didn't have to be there then. We can go and pick them up now. That's us sampling them in a pit. That's the ship, the vessel that brought us there. There's no trees. It's an amazing place. And when we climbed up to the crater, we basically had the past 10,000 years record laid out in front of us, and we could sample the whole history of the last volcano. And we bring back these samples of volcanic cinders and ash from the explosive eruptions, and then look at them under the microscope. This is me looking at the microscope. It's most of my students and postdocs do the work. They laugh when they see me in the microscope. I do know how to do it, but it's a lot of work. These are giant olivine crystals. Most of them are the width of your hair. They're really small crystals, and then we're looking for inclusions inside those crystals. So really small inclusion on the order of tens of microns usually. But that's enough with modern, fantastic instrumentation that we can get a laser beam or an ion beam or an electron beam. All 3 of those things can actually sample and determine major elements, trace elements, and the volatile species all in a single little bleb of glass like that. It's quite remarkable. So we can do almost the whole periodic table in this little tiny bit of precious magma that's been trapped inside the crystal. This is what the data look like. So each one of these data points is one of those melt inclusions inside an olivine crystal, and this is from the eruption that we just went to sample at Seaguam volcano. We're looking at water versus CO2, and CO2 actually has an even lower solubility in magmas, and so it's the first thing to degas as magmas rise and decompress, and then the water degasses. So really as magmas rise, they're losing their CO2 and then they lose their water. But this enables us to argue that this magma originally had at least 3.5 weight% water in it, which is a ton. This is a major species in the magma. And the question is that a lot or is that a little? Is that a lot of gas or not? And this is what we've really spent the last 10 years on. And I'll let you look at this. Here's Seaguam, VEI-1 eruption with 3.5% water. That was one student's thesis. Here's Fuego volcano in Guatemala. It's an eruption that's 3 orders of magnitude larger. You can see it. It's a big eruption. And there's 4.5% water. That's another student's thesis. And we've looked at a bunch of volcanoes, and we don't see a big range in water. Okay? We would expect huge differences if this was the driver. In fact, I've just written a review paper that shows most magmas have around 4% water in them. After looking at 56 different volcanoes, we see quite a strong mean around 4%. Sure, there's some variation. There's a factor of 2 or 3. But this is not nearly enough to explain, from just the seltzer bottle point of view, more water, more eruption, or more explosive eruption. And I'm actually going to talk about this to some degree tomorrow in the Earth Science seminar. So we have to go back to the drawing board and think about the physics again. And so we go back to the seltzer bottle, and what if we don't want it to erupt explosively? What would you do? Well, you know what you would do. If I handed this to you you'd go, and then you'd go, you'd open it really slowly. So the rate must be important. Okay, the rate, it probably is just as important. How rapidly we decompress. And that's really what we're investigating now. And this is something we've known very little about, are the time scales. So this is kind of how the problem would work of now slowly uncapping the seltzer bottle or uncapping it quickly. Of course, we're not uncapping anything on Earth. What's happening is the magma forms deep in the mantle. It's buoyant, and so it rises. Especially once it starts exhaling gas, it becomes even more buoyant and rises and erupts. So that's what's happening. It might stall along the way in magma chambers, but it's rising. And as it rises, it's actually decompressing. The pressure comes from the overburden of rocks above you, just like when you're deep in the ocean, the pressure comes from the water over your head. So it's at high pressure here and low pressure there. So as it's rising, you're basically uncorking it. And that's what causes the gas to come out. So what we're wondering here is if the rate at which it ascends matters. And to test that, we need a clock. And this is a tricky clock. These are in geology, we have clocks that are based on half-lives of isotopes. We can date things that are billions of years old and tens of thousands of years old. But it's very hard. This is something that we think happens on the order of minutes, days, months, maybe a year. So really short time scales. So we've had to come up with a different kind of clock. We're going to use crystals because they are what form when the magma is cooling in this process too. It's crystallizing. So the crystals, they bear witness to the whole path. And so if we can date them, they can give us an idea of how long this process takes to uncap the seltzer bottle. So the analogy here of what we use is the turkey. Actually, Lesley's going to recognize her collaborators here. They actually wrote a very serious science article in Physics Today about thermal diffusion in turkeys. They were trying to prove that Lord Kelvin got the age of the Earth wrong because he didn't deal with convection, he only dealt with conduction. But it's a good example of what we're doing. So if you take a turkey out of the oven, let's say, and stick it immediately in an ice box, the ice box will say is perfect and it's kept at 0 C, what will happen? So the turkey will cool off. Initially, it will stay hot in the middle, at let's say 180 F, and then it will cool off at the edges. And we could calculate how much it cools off if we know the rate at which heat diffuses through a turkey. And if we know that it's around 2 centimeters in 20 minutes, that would be the calculation for a turkey, or 4 centimeters in 80 minutes. This is, by the way, why you take your turkey out and let it sit for a while, because it's still hot for an hour inside and cooking on the counter. It's also what people use to figure out how long bodies have been dead by looking at their thermal diffusion profiles. So if your life depended on figuring out how long the turkey had been sitting in the icebox, you could figure that out by sticking a temperature probe in and measuring this temperature profile, and then applying this thermal diffusion model to figure out whether it was closer to 20 minutes or 80 minutes or longer, and the core temperature will start to drop if it's longer. So thermal diffusion is a useful clock. This is a clock to date your turkey. We're going to use chemical diffusion, which is the same process recorded in crystals. The advantage is that chemical diffusion is preserved in the crystal long after the magma's cooled, because chemical diffusion gets frozen in at low temperature. So we can go back at any deposit and look at chemical diffusion and figure out how long the magma was cooling and decompressing. So the way that would work, here's a crystal bathed in a magma at equilibrium, so it's all one temperature, just like when the turkey's first in the oven. If we measure the chemical gradient across the crystal from edge to center to edge, it should be homogeneous if it's sitting, let's say, for a long time in a magma chamber or a long time in the mantle. If we change the external conditions, like sticking it in the icebox, or if we cool it, or we mix the magma, or we change the pressure, or we degas it, then the outside magma responds much more quickly, but the crystal takes a while because chemical diffusion inside crystals is slow, so it's going to leak or equilibrate slowly, and it will actually show profiles that are just like the turkey profile, and we can use this then as a clock to tell how long the crystal sat in the magma at magmatic temperatures to re-equilibrate. The way this would work again is you take a crystal and analyze a chemical profile, and if you know the diffusion coefficient for that species, you could match it up with the appropriate curve and say, okay, this crystal last equilibrated 5 hours, the conditions last changed 5 hours ago, and it had that much time to re-equilibrate. So I'll give a couple examples of this and what we're doing with it from my group, just to finish up. That here's one that we're going to call the highway from hell. And what this is ultimately clocking how fast magma is getting from its source in the mantle to the surface. What we're looking at, again, are crystals. And you can even see in this crystal, it's zoned in the grayness. It's a little grayer in the core and darker in the rim. That's actually chemical zonation. It's a ghost. And we'd like to know that's a relaxation from the core to the rim, and just like the turkey. And we'd like to measure the thickness of that rim and find out how long the crystal's been equilibrating from its last equilibrium, in this case in the mantle. We're looking at very primitive crystals in this case. This is work by Philip Ruprecht, who was a postdoc with me and is now a research scientist. And this is actually going back to Irazu. He's been working on Irazu volcano. This is the volcano where, like, I saw God and heard the lecture from Barbara Barrero about beryllium-10. Somehow I've gone back to Irazu throughout my career. I've published 3 papers on it, not really expecting to. But Irazu is amazing. It's got tons of crystals in it, some of which come all the way from the mantle. And Philip demonstrated that by looking at the mineral olivine, and he did that by measuring chemical profiles. So here's the core of the crystal in the rim, and there's a profile in the black curve, which is the iron-magnesium ratio, but the one that he's looking at is in nickel. The nickel metal content in the olivine shifts from here suddenly up to here, and he proposes that this mixing of 2 different magmas in the mantle, because this is all happening under conditions that are appropriate to the mantle. And initially it was a step function, but it's relaxed diffusively again. And by applying the diffusion coefficient, he comes up with a time scale on the order of months. That this crystal was last in the mantle where magma's mixed, and then it was allowed to, it could only have re-equilibrated months. If it had been years, this would all be chemically homogenized. It would be a flat crystal. So that's why we're calling it the highway from hell. It only takes months to get magma all the way through the crust to the surface. This eruption went on for 2 years. So the fact that this can come from the mantle in months is completely unexpected. We think that, that the source of the magma must be the ultimate trigger for a volcanic eruption. People have proposed this, but nobody's actually seen the source coming from the mantle. It's very difficult to see with earthquakes, and before these kinds of crystal clocks, we didn't know crystals came that rapidly from the mantle source to the surface. So this is new work that is coming out in Nature, actually, because what it's arguing is that we really need to set our sights deeper when we monitor volcanoes. Most people look just up at the magma system, but now we know they're being recharged all the way from the mantle. We need to set our sights to deeper levels. In fact, during the Eyjafjallajökull eruption, there's billions of earthquakes up here in the top few kilometers of the crust, but when you filter those out and very carefully locate them, seismologists found earthquakes that do extend all the way down 30 kilometers, again, to the mantle under the volcano, and that these were popping off at different weeks in May, so suggesting that magmas can move rapidly on the timescale of weeks and months under the volcano to supply it. So that's one crystal clock we've been working on, which is kind of the recharge, which could cause volcanoes to wake up or cause them to trigger and cause them to be sustained. But the other thing that we're interested in is more really opening the cap of the seltzer bottle fast. And that is, we'll call that the shot out the cannon. And that's what happens just at the very end. And for that, we need a super fast clock, something that really is going to look at timescales of minutes. And for that, about the fastest diffusing species we can find is water itself, which is dissolved as protons ultimately in glass and can move very quickly. This is a crystal with tubes of melt that are connected to the outside bubbly melt. But the water that's in here is trying to reach a bubble and doing that with more or less success on how much time it has. So we can use that as another diffusion clock. This is work by my graduate student, Alex. And we're studying a big explosive eruption here, Fuego, which this was just September of this year. 15,000 people were evacuated during this eruption. So it's had quite explosive eruptions over the last few decades. And we're working with Eric Howry at the Carnegie Institution of Washington because he's got the nano SIMS, which enables us at 5-micron spot resolution to measure water, CO2, sulfur, fluorine, chlorine species along one of these melt tubes to look at the profile of how water is diffusing out towards a bubble. The diffusivities of water are so fast that the timescales we're looking at are minutes. So this is a 150 micron melt tube, and this is the water concentration. The little dots are our data, and those are 3 different models. This is actually the turkey getting cold in the core. So we know the initial water content from melt inclusions. We know that this in the tube is dropped all the way down here. It's on its way to totally cooling, and that's about 10 minutes of time. This is remarkably fast. This means this part of the shot out the cannon's happening about 30 miles an hour. It's during the eruption, so the magma's getting from the magma chamber to the surface in tens of minutes. Now that's for an extremely explosive volcano. I just showed you that. The theory would be if we opened the cap more slowly, then it should be less explosive, and you can see where we're going with this for the next 5 years. So yeah, why are some volcanoes more explosive than others? This would be the exam take-home point if you were taking my class. Volatiles, viscosity, and velocity, so the 3 V's. We know a lot now about how much water's in magmas. Their viscosity is important. It's how sticky the magma is, and we know a lot about this from temperature, but it's this velocity term that we're working on right now. So you could join me. I've got 3 other people in the group who are all working on this. Dave's working on Kilauea, Elizabeth's measuring diffusion in the lab, and Claire is looking at a different mineral, clinopyroxene, which has a different clock. Because we have a lot of work to do. How many volcanoes are erupting right now? Anyone want to guess? Like this week? 10? 10's a conservative guess. There's usually 15 to 20 at any given time. But it came from the dean. I think 10's a good guess. This is this week, May 15th. There's about 16, I think, that are erupting now. Many in the news in the past few days. Turrialba's right next to Irazu. It just woke up this week. The Philippines has killed some people. The volcano there, my own. Popocatépetl's erupted and covered Puebla, a city of 4 million people, in ash. And then my favorite is Pavlov, so back to the Aleutians. Pavlov is erupting and we're diverting aircraft. At the same time, Cleveland's erupting and there's no monitoring sites on Cleveland. So we're back to Alaska and its airspace coming full circle to really think about monitoring, getting people out of harm's way, but also what really sets the course for the most explosive volcanoes. What triggers their eruption and what causes some to be more explosive than others. Thank you.
One or 2 questions? Any burning questions for Terry?
Yeah.
You figured out any way to harness the energy of volcanoes?
Well, there's geothermal energy, of course. I mean, it's not really the energy of the eruption. I don't think that's going to be really easy to do, because when you calculate, the total energy change in moving that much rock in an explosive eruption, it's the equivalent of multiple nuclear bombs. So it's a great force of destruction, but I don't know how one would harness that. But certainly geothermal, it's all a manifestation of the Earth cooling off. The Earth is going to cool off. We can't stop this from happening. There are going to be volcanic eruptions. So yeah, we can harness the heat. But I'm not aware of any feasible way to harness that amount of energy. Maybe from a Hawaiian type eruption or something.
How many of these volcanoes are the type you were particularly studying? The plates, moving plates?
How many of these exact ones? I've worked on Pavlov, Popocatépetl, Turrialba, and I think this is my own. I've actually worked on all 4 of these, but I only know the water content in Pavlov and Turrialba. And someone else has worked on Popo. Yeah, these are some of the greatest hits volcanoes. They've been erupting, all of these have erupted in the last decades, kind of recurrence. So they're well-studied volcanoes. But some of these, like there's some Papua New Guinea. I don't know what those are, the ones in Colombia. There's Hawaii, of course. There's 40 alone in Alaska, so we've studied 7 of them. We really haven't scratched the surface on most of these. And we're not even monitoring a lot of them. So that's really the problem. Yep.
This is the last question we have time for because we've got a poster session.
The Hawaiian volcano, you're not sitting over subduction.
That's
So
true.
How does that play in your?
Yeah, it's in the middle of the plate, like you can see. So it's a hot spot volcano, like Yellowstone, like Iceland. Well, Iceland's on a mid-Atlantic ridge. The conventional wisdom is that there isn't as much water because, again, the subduction zone volcanoes, the subduction zone is supplying the water. And that's why the subduction zone volcanism is generally more explosive. But like I said, the Kilauea actually was explosive in the last century. And we've just measured a weight percent of water, which isn't nothing, considering in these really explosive ones, we're measuring 3 and 4. So I'm not convinced the water idea is the right one. It might be it's hotter than normal. The magma is extremely hot. It's very low viscosity. It's very fluid, and maybe that's why if you maintain that high temperature, then you don't have an explosive eruption. So we're working on temperature too. Silly as that sounds. You need thermometers. It's not trivial to figure out how hot magmas are before they erupt.